A very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be talking about the Cauchy stress tensor. So let us get started. The topic for today's lecture include a discussion on the Cauchy stress tensor. Although we defined the Cauchy stress tensor last time, today we will try to understand this in a bit more detail. We will first show that sigma, which is the Cauchy stress tensor, is actually a tensor. And then we'll talk about the cube picture of stress, which is typically shown and sometimes confuses many people. So let us get into the first topic. So let us have a quick recap about the Cauchy stress tensor. In the last lecture, we talked about the Cauchy stress formula. So let's say we have a body, part 1 that we've been talking about, and we have a point P. N hat is a unit normal that denotes the cutting plane which passes through P, which is shown as the shaded region. And we showed that the traction vector, which acts because of the part 2 on part 1, is written as vector t with a superscript n hat. And this traction vector need not be in the n hat direction. So to define the state of stress using finite amount of information, we developed the Cauchy stress formula, which states that the traction vector on an arbitrary cutting plane n hat can be written as a linear combination of traction vectors on coordinate planes like this. So if we have the information about the traction vector on the coordinate planes, that is E1 plane, E2 plane and E3 plane, then we can find the traction vector on any arbitrary cutting plane with a normal in the n hat direction. This is a very powerful relation because this allows us to store the information about the state of stress at a given point P using a very small amount of information, which is basically just these three traction vectors on three mutually perpendicular cutting planes. And this allowed us to define the stress tensor, which was defined as sigma ji is given as Ti superscript Ej. In the symbolic notation, we can write the Cauchy stress formula as simply the vector n hat is n dotted with sigma, where the sigma is defined like this. Now this formula is very interesting in the sense that if I look at the initial notation here, what I see is that I can write T1 on a cutting plane n hat as T1 E j hat and j, which when we expand gives T1 E1 times N1 plus T1 E2 times N2 plus T1 E3 times N3. So let us look at what we've got here. So this tells us that, well, the first component of the traction vector on the n hat cutting plane is a linear combination of the first component of traction vectors on three mutually perpendicular cutting planes or the coordinate planes. And the weights are simply the three components of the normal vector that is given to us as the cutting plane. And the stress tensor sigma, or the Cauchy stress tensor sigma that we have defined, is nothing but the three traction vectors on the three coordinate cutting planes. That is, sigma 1 1 is T1 on the even plane, sigma 1 2 is T2 on the even plane, sigma 1 3 is T3 on the even plane, and so on. So this is a very powerful quantity because this allows us to calculate the traction vector on any arbitrary cutting plane with a normal in the n hat direction. Now we've been calling sigma as a tensor, but we haven't shown whether this quantity that's containing these 9 components is actually a tensor. So let us now show, using the idea of transformations, that the quantity sigma, which contains these 9 components, which are basically the 3 traction vectors on 3 coordinate cutting planes, is actually a tensorial quantity. Now, how do we show if a quantity is a tensor, particularly in this case, a second order tensor? We discussed earlier that the way we show a quantity to be a tensor is that if that physical quantity satisfies the mathematical tensor transformation property. So our job is to show that the quantity sigma ij satisfies the tensor transformation property. So if we can show that, that is that the physical quantity sigma satisfies the mathematical tensor transformation property of the tensor transformation rule, we have shown that sigma is indeed a tensor. Well, our starting point is a traction vector in the n hat plane, because it was this traction vector which allowed us to define the stress tensor sigma using the Cauchy stress formula. Now I'm calling sigma as a tensor in the discussion because I already know it's a tensor. So you must please allow me to use the word tensor, although in this exercise we are actually trying to show that the quantity sigma is indeed a tensor. So the starting point is the traction vector along the n hat direction and the Cauchy stress formula. So we'll accept these two, that is, we accept an understanding of the traction vector on the n hat plane, which was defined using the Cauchy stress principle and the Cauchy stress formula, which allowed us to write T n hat as sigma ji and j. Now the traction vector along the n hat cutting plane can be written as TIEI if I was expressing this in the O, x1, x2, x3 coordinate axes. Let me draw that. I'll also draw a rotated coordinate system, which is Ox1 prime, x2 prime, and x3 prime. And whenever we talk about transformations, we basically talk about finding the components of the quantity in the rotated or the primed coordinate system. So in the rotated coordinate system, the traction vector would be written as Ti prime, because the components will change, and then the superscript vector will also be represented using n hat prime, and the 3 basis vectors will also be written as ei hat prime. So this is in the O, x1 prime, x2 prime, and x3 prime coordinate system. Now remember, this vector does not physically change if I rotate my coordinate system. So if I had a vector pointing like this, let's say this was traction vector t, then the vector will still be the same. It is just that if I look at the vector from the prime coordinate system, its components will be different. So the components are different, definitely, but when I multiply them by the basis vectors, which are also different, I get the same vector on both sides. So I can write this equality. And this is going to be the starting point for our proof. Now I'll apply the Cauchy stress formula let's call this as 1. This Ti n hat Ei becomes sigma Ji nj Ei. So Ti n hat becomes sigma Ji nj, and this is equal to, we have Ti prime n hat prime Ei prime. So this Ti prime actually becomes sigma Ji prime nj prime times Ei prime hat. So this is the idea that sigma prime would be a physical measurement of the 9 components if I measured them in the primed coordinate system. Now we know that nj prime and Ei prime are vectors. That's a known fact. So we can transform these in the non-primed coordinate system, because our aim is to somehow cancel it with these. How do we do that? We write the vector transformation property. So nj prime can be written as a j p times np, and we can write Ei prime as a iq eq hat. Okay, so this is from the vector transformation property. Let's call this equation 2. So I substitute the above in equation 2. So this is going to give us, well, the left hand side stays the same, and the right hand side we have a sigma ji prime, and then the nj prime becomes an ajp np, and ei prime becomes aiq eq hat. So I'll move all the a's to the left, ajp aiq, then I have a sigma ji prime, and then we have an np times eq. Now we will play around or modify the indices on the left hand side, because I want to make sure that the index of this n and the index of this n is the same. And I can do that because the index of the n on the left is j here, which is a repeated index. So I can very well write this as sigma pi np times ei hat. They're exactly the same. And similarly, I can also in fact modify the I to a q here, because these were repeated as well. So now we can see that we have an NPEQ and we have an NPEQ on the right hand side as well. So I'll move everything to the left now. So this is equal to 0. So now this can be written as sigma PQ minus AJP AIQ sigma JI prime times NP times EQ hat equals a 0. So we have a product of two quantities which is equal to 0. And I know that NPs are not 0 because they denote an arbitrary normal n hat which denotes a cutting plane. And EQ hats are also not zeros because they are simply the basis vectors in the coordinate directions. So this means that this quantity in parentheses has to be identically 0. So this can be written as sigma PQ is AJP times AIQ times sigma JI prime. And this is in fact the initial form of the tensor transformation property. So this is the reverse transform, which allows us to write the sigma components in the non-prime coordinate system in terms of sigma components in the prime coordinate system. If you want to see the symbolic form, this is much easier if you write it in this way. So I write this as the Pj component of A transpose times a sigma Ji prime times AIQ. So we can see that this Jj and this II are contiguous. So this denotes a multiplication. So we can write sigma as A transpose sigma prime A. So which is the symbolic representation of the tensor transformation property. So we started with the knowledge of the Cauchy stress formula, which was the formula that allowed us to define sigma. We applied the idea of vector transformation property to quantities which we know are vectors, and this resulted in the tensor transformation rule for sigma, which is exactly the same as what we have for second order tensors. So this proves the fact that the quantity sigma that was defined using the Cauchy stress formula is indeed a second order tensor. So this completes our discussion on showing the fact that sigma is a tensor. So now we can confidently use the statement that this is a stress tensor. The next topic for today's discussion is the cube picture of sigma. So let me write the components of sigma, which are as follows. Now these are, as we have discussed, the traction vectors, which is T E1 hat, T E2 hat, and T E3 hat. That's the definition of the Cauchy stress tensor sigma. So these three vectors are defined at a given point P. So what we had shown was that if this is the point P we are talking about, and this is the n hat, then this is the traction vector n hat, and we had drawn three cutting planes. One was along E1 hat, one was along E2 hat, and one was along E3 hat, and we found the traction vectors on these three cutting planes. But all these planes were passing through the point P, and the traction vectors were found on this point P. It's an important point to note that all three traction vectors, which are TE1, TE2, and TE3, defined on point P, as the three cutting planes pass through the point P. So if I was to draw this, I would draw the three cutting planes like this. So this is the cutting plane passing through the point P, which has a normal in the E1 hat direction, and the traction vector would be something like this, which is T on E1 hat. This is the point P. So I'll have another cutting plane which is passing through the point P, like this. And this cutting plane has a normal in the E2 direction, and the traction vector would be something like this. Then we have a third cutting plane, which is a normal in the E3 direction, which we'll draw like this. So this is the normal, and the traction vector would look something like this. So I hope you can imagine the three mutually perpendicular planes here drawn in red, green and blue colors with the corresponding unit normals along E1 hat, E2 hat and E3 hat, because these are coordinate cutting planes, and the traction vectors which could be in any arbitrary direction, not necessarily along the normal directions. Now if I was to decompose this T or these three traction vectors into their three components, the figure would become quite difficult to resolve. So what we do is, for convenience, purely convenience purposes, we draw a cube. So this cube is drawn in such a way that we have this cube having a red plane in the E1 hat direction, whereas in the E2 hat direction, I have another face of the cube, whereas for the E3 hat direction, I have a third face of the cube. So now you can see that in this cube, the points from which the normal originates and at which the traction vectors will be defined are all three different points, which is incorrect because it is through the point P that the three component or the coordinate planes pass. But we do this because this gives us more space to write traction vectors. In fact, if I had to write the three components of traction vectors on the three planes, I could easily do that now, because let's say on the E1 plane, I have a component of traction vector along E1 direction. So I'll call this T1 on E1, and I'll have a component of traction vector along the E2 direction, which is this one. So that's T2. Superscript is still E1 because they're defined on the E1 plane. And then I have a third component, which is T3, defined on the E1 plane. Similarly, I could write the three components of traction vectors on or defined on the E2 and the E3 planes like this. So this figure looks much neater, but I'll mention this fact in writing, that this cube picture is incorrect, as the tractions are defined at the same point P. Also, the three cutting planes, or the three coordinate cutting planes, pass through the same point P. And here you can see that these coordinate cutting planes do not all pass through the same point. In fact, there is, well, the points with the traction vectors are defined, they're all three different points. So the picture I had drawn above, which is this one, is more correct. But this does not leave us any space to write the components of the traction vectors on the three cutting planes. Now, why are we writing these three components? Because these three, or 3 plus 3 plus 3 in this case, 3 on each face, are nothing but the components of the Cauchy stress tensor sigma. So I'll show you the same cube picture, but instead this time it will be written with sigmas. So in this figure, on the E1 hat plane, we have sigma 1 1, which is nothing but T1 on the E1 hat plane. Then we have a sigma 1 2 and sigma 1 3. This is because we had defined sigma ji as Ti Ej hat. So the first index is the index of the cutting plane, and the second index is the component of the traction vector. So on the E2 plane, which is the green plane, we'll have sigma 2 1, sigma 2 2, and sigma 2 3. Again, the first index of sigma denoting 2 in this case because it's on the E2 hat cutting plane. And then on the E3 hat, that is the blue cutting plane, we have sigma 3 1, which is the first component of the traction vector on the E3 hat plane, sigma 3 2, and sigma 3 3. And you would definitely see this kind of a cube picture which is used to represent the stress tensor. Now I'm sure you appreciate the fact that this is nothing but the 9 components of the stress tensor, but this picture is not strictly correct because stress tensor is defined at a given point P. All these three planes should be passing through each other and intersecting at the point P. Now, if you look at this picture, you will notice that sigma 1 1 is along the even hat direction. Similarly, sigma 2 2 is along the E2 hat direction, and sigma 3 3 is along the E3 hat direction. So these three, that is sigma 1 1, sigma 2 2, and sigma 3 3, are called normal stresses because they act normally to the plane or along the normal to the plane. And the other 6 components, that is sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 3, and sigma 3 1, sigma 3 2, are all shear stresses. Because they act in the plane on which the traction is acting. So they create some sort of a shearing on the plane. We'll discuss more about it, but this is a terminology that we must remember. And in the normal stresses, if the normal stresses are positive, that is in this case, as I've shown, sigma 1 1 is a long even hat. So this tends to expand the cube. So they're called tensile stresses. And if the normal stresses are negative, if the sigma 1 1 was acting inside, then this would try to compress the cube. So they're called compressive. So depending on the sign of the component in the normal stresses, that is sigma 1 1, sigma 2 2, and sigma 3 3, they would either be tensile or compressive. Now please remember that this sigma is defined at a point. But as you change the point, as you move around in space, you would see that sigma will change. And that is what makes the subject interesting, is because we would want to know what the stress field looks like. So it could happen that at one point you have tensile stresses in one direction which become compressive if you move around in the space. But since this course is on the foundations of quantum mechanics, we will not go deep into the different kinds of objects and scenarios. Our goal is to develop a concrete understanding of different physical objects like stress in this case and geometrical quantities. So we are focusing more on the ideas and not on realistic materials in this course. In advanced courses, depending on whether you go into fluids or solids or other kinds of materials, you will be studying more into the detail of those materials. So this brings us to the end of this lecture. And here is a problem for concept check. So it is asked that you have to write the three equations in the Cauchy stress formula. That is, you have to expand the traction vector components T1 n hat, T2 n hat, and T3 n hat in terms of sigmas. And you should then look at or see how there is a linear combination happening in the three traction components written for the n hat plane. So thank you, and I will see you in the next lecture.